In this video, we consider the Biot-Savart Law, which is an equation describing the magnetic field generated by a constant electric current. It relates the magnetic field to the magnitude, direction, length, and proximity of the electric current. When we were working with electric fields, we used forms of Gauss's law formulated to accommodate point charges, as well as charges distributed in lines, across surfaces, and through volumes. Analogously, we have used a form of the Biot-Savart Law to describe magnetic fields, appropriate for steady currents moving in lines, such as when current flows through a wire. As shown here, this is the form that we would use for current flowing through a wire. There are other forms of this law that may apply in other situations. For example, when there is a surface current, we use a form that includes K, the surface current density. When there is a volume current, we use a form that includes J, the volume current density. However, although it seems like this would be the correct form, there is no form of the Biot-Savart Law that we can use to describe magnetic fields produced by individual point charges, even if they are moving. The reason for this is that individual point charges, even when there are many of them, do not constitute a steady current. As we have just seen, there are a number of ways to express the Biot-Savart Law mathematically. We are going to focus on the magnetic field generated by a steady current moving in a line, typically confined to a wire as shown in the figure. The current is expressed as a vector with both magnitude and direction. We observe the magnetic field at the field point P, somewhere outside the wire. The magnetic field is a function of R, or a position with respect to a reference point that we establish, typically the origin. To find B at the field point, we consider the infinitesimal wire segment dl. The contribution to the overall magnetic field B is the current I, a vector quantity, crossed with the separation vector script R shown in the figure. Here. We take this and divide it by the magnitude of the separation vector squared. The separation vector is different for each infinitesimal line segment dl. We sum over all these contributions to find the magnetic field at P, which is a distance r away from the origin. This expression includes mu sub 0, which is here shown the permeability of free space, a constant of proportionality that exists between magnetic flux density and magnetic field strength in a given medium. In this case, the medium is free space. It is analogous to epsilon 0, the permittivity of free space, which we find in Coulomb's law and other expressions dealing with electric fields. The direction of the magnetic field is determined by taking the cross product of the current and the separation vector. For current flowing through a wire, this means that we use the right-hand rule to find the magnetic field direction. The thumb of the right hand points in the direction of the current, and the fingers curl around the wire, indicating the direction of the magnetic field. In the figure shown, the direction is position dependent, pointing counterclockwise around the wire. This direction holds for any point along the wire, any distance from the wire. Using the Biot-Savart Law, we want to find the magnetic field due to current flowing in a portion of straight wire at a field point P. This is the segment that we're interested in. The field point P is a distance s away from a long wire. One end of the wire portion is at angle θ1 from the dashed perpendicular line that marks the shortest distance between P and the wire. The other end of the wire portion is at angle θ2 from that same dashed perpendicular line. In all cases, this is how we measure the angles θ1 and θ2. They are measured in reference to this perpendicular. The details of the integration can be found in Griffith's Introduction to Electrodynamics, 4th edition, on page 227. The result is presented here. The magnitude of the magnetic field is mu0, the permeability of free space, times the current I, divided by 4 pi s, where s is the perpendicular distance of the field point to the wire. And this quantity is multiplied by the difference between the respective signs of theta 2 and theta 1. Since the current is flowing to the right through the wire, we know that the direction of the magnetic field at P will be pointing out of the page. Now let's say that instead we want to find the magnetic field at Q, which is directly below P, at a distance s away from the wire, the same distance that P is from the wire. At Q, the magnitude of the magnetic field is the same, but the direction is into the page. Next, let's find the magnetic field at P due to a current running through an entire wire of infinite length. In this case, theta 1 is minus 90 degrees, and theta 2 is plus 90 degrees. This means that the magnitude of the magnetic field works out to be mu0 times I over 2 pi s. The direction of the field at P is out of the page as before, and it is given by phi hat, since B is described using cylindrical coordinates. As we stated before, when current is running steadily through a straight wire, we can use the right-hand rule to help us find the direction of the magnetic field. The magnitude of the magnetic field is proportional to the magnitude of the current, and it is inversely proportional to the distance that the observation point is from the wire. This expression is a valid approximation of B for a long straight wire where the length is much greater than the distance between. Now let's consider what happens when we place two current-carrying wires near each other. The wires in question are straight, parallel to each other, very long, and very thin. The wires are far longer than D, the distance that separates them. The current flowing through the upper wire induces B sub 1, while the current flowing in the lower wire induces B sub 2. Additionally, the current in the upper wire responds to B sub 2, while the current in the lower wire responds to B sub 1. It is in this manner that the currents interact. We choose P1 and P2 to be field points on wires 1 and 2. Those are just chosen arbitrarily. The point is that they don't have to be immediately one above the other. They're just two field points. But these are the field points that we've chosen. The magnitudes of B1 at P2 and B2 at P1 are described using the equation we've already used. The direction of B1 at P2 is into the page, and the direction of B2 at P1 is out of the page. Let's look at how a magnetic field due to a given wire, say wire 2, affects wire 1. We can use the Lorentz Force Law, here shown in a general way, to describe the magnetic force due to magnetic field B2 acting on wire 1. Given that wire 1 is straight, we can use this equation to compute that force, but since the wire is effectively infinite in length, the total Lorentz force is infinite. It's more meaningful to calculate the Lorentz force per unit length. The Lorentz force per unit length acting on wire 1 is constant, proportional to the product of the two currents, and inversely proportional to the distance between the wires. It is in the downward direction. So wire 1 experiences a downward force. We can carry out a very similar computation to find the magnetic force per unit length due to the magnetic field B1 acting on wire 2. It has the same magnitude, but is in the upward direction. What this means is that wire 2 experiences an upward force. FB12 and FB21 are equal in magnitude and opposite in direction, and they are both proportional to I1 and I2. They diminish as the wires are placed farther apart, and μ0 is a scaling factor. These results hold when the two currents are moving in the same direction. If we reverse the direction of one of the currents, the directions of both forces are changed. This means that parallel currents, that is, currents flowing in the same direction in parallel wires, experience attractive force. The wires are drawn together. On the other hand, anti-parallel currents experience repellent force. That is, the wires are forced apart. But how strong are these magnetic forces? We can get an idea by looking at a specific example. Suppose both our parallel wires carry currents of 1 amp and that they are placed 1 meter apart. The magnetic force per unit length of B1 acting on wire 2 is 2 times 10 to the minus 7th newtons per meter, which is not very strong at all. In fact, magnetic forces in wires are typically much weaker than electrical forces. Now let's apply what we know about finding magnetic fields due to steady currents to solve the following problem. Suppose we have a square loop of wire that carries a current I flowing counterclockwise in the loop. We'd like to determine B at the field point P, which is in the center of the loop. The perpendicular distance from P to any one of the wires is R. We find the total magnetic field B using superposition, calculating the magnetic field induced by the flow of current in each straight piece of wire one at a time, and summing the results. Let's start with a segment of wire at the bottom of the loop. The straight line distance from P to the wire is capital R, and the angles theta 1 and theta 2 measured from R are minus 45 degrees and 45 degrees respectively. We calculate the magnitude of the magnetic field using the expression that we saw earlier, and we find that the magnetic field B due to the bottom segment of wire is mu naught I over 4 pi r, all times the square root of 2. And the direction of B at the field point P, according to the right-hand rule, is coming out of the page. By symmetry, we see that the magnitude of B will be the same for all three of the other segments of wire, and that the direction of B at P will also be coming out of the page for all three. This means that the total magnetic field is 4 times the field due to the bottom segment of wire coming out of the page. We can use this approach to find B for current carrying wires of other shapes as well.